Okay, in this video we're going to talk about sort of the foundation for the logic of hypothesis testing. And it starts with something called the Central Limit Theorem, which we'll get into in just a second. But let me set this up a little bit. What we're doing is we have populations that we sample from, right? So we're going to draw from this population a sample. And if we did draw from the same population, the samples would be pretty similar to one another, right? The sample 1, would be similar to sample 2. And in fact, this situation represents what would be true if our null hypothesis was correct, in that there's no difference between our control and our experimental group, or two groups are very similar. Their behavior hasn't changed, right? So that would represent this particular situation. If, on the other hand, our experimental manipulation works, well, the way it would represent is that the two groups would be different, and they would be different enough that they would appear to come from different populations, such that they're characteristically different in some kind of way. So that the behavior is altered, doesn't belong to the same population. And if that's the case, you know, they're not the same, they belong to different populations. That would be, when we get evidence to reject the null hypothesis, that's in effect what we're concluding. The two samples are so different that they couldn't have possibly come from the same population. Now, this is based off of something known as the Central Limit Theorem. And the Central Limit Theorem essentially says that if you draw from the same population over and over again and look at a distribution, a group of sample means, that it will be normally distributed. So let's keep some of this. So let's suppose that the null hypothesis is indeed correct, and that we're sampling from the same population over and over again. What the Central Limit Theorem says is that if you create a distribution, so we're going to create a frequency distribution here, right? So here's the, so frequency is over here on the y-axis, and the actual sample mean values are down here on the x-axis. And so what it means is if we created a little, so we have our first sample mean, and then we put our second sample mean, and we keep doing this. We keep sampling over and over again, and we plot the frequency of our sample means. What we would see is that we would have a lot of them that line up around the true population mean mu, and such that if you draw a distribution, it would end up being normal. And if it's normal, then we can estimate the likelihood that any two samples come from the same population by using our normal curve information, right? Remember, between plus and minus 3 standard deviations, right? We had 99% of our scores in the distribution. Well, the same is true if our sampling distribution, a group of sample means, is normally distributed. Ones that fall out here are going to be very rare. Well, that's contingent upon, excuse me, that's contingent upon this distribution, the sampling distribution, actually being normal. And how do we know that? Well, we know that from the Central Limit Theorem. The Central Limit Theorem says that it's going to be normal. So let me show you this in action. So this is a computer demonstration of the Central Limit Theorem. And so what we have is we have a parent population here. This is a normal distribution, and the computer is going to draw random samples from this. It'll actually draw 5 random samples and plot the mean value here, creating a sampling distribution. It's going to do that again here, and then it'll actually draw 16 times down below. So it's drawing 5 times, it's going to draw 16 times, and then plot down below, right? And we could do this again. We'll do it again, and it'll retain the information, right? So there's the second plot. So now it's going to sample 16 times, create a group mean, right, and plot it. So we can do this again and again and again. Let's do it like 10,000 times. And what you see is you get a normal distribution. What you see down here is even more normal distribution. So our sampling distribution, our mean of samples drawn from this population, our group of sample means is normally distributed, right? And the cool thing about the central limit theorem is that the parent population does not have to be normal for this to be true. So let's create a skewed distribution, right? And if we do this, so we're doing the same thing, right? And we do 10,000 times, still normally distributed, even though this is a skewed distribution. The sampling distribution will be normally distributed, right? That's what the central limit theorem says. Uniform would be rectangular, so it's like everything is equally frequent, right? Still get a normal distribution. And what if we even create our own, what if we had like a bimodal distribution, right? Two different modes, right? And we draw, right? It takes a little bit more samples here, but you're still getting a normal distribution, right? So the cool thing is the parent population does not have to be normally distributed for this to be so. The central limit theorem says sampling distribution will be normally distributed. So what does that mean? Let me reemphasize that. I kind of said this over here, but that means that if we draw from the same population, we can put these populations on the same frequency distributions. It will be normally distributed, right? Our sampling distribution will be normally distributed. And that means that most of, let's say between plus and minus 2, we'll say 95, that would be minus 2, right? Minus 2, not plus 2, standard deviations. And over here, plus 2 standard deviations, right? We're going to have like close to 95% of all the sample means from that population are going to be here, in between plus or minus 2 standards. So that means that if our sample mean falls way out here, that it's unlikely to belong to that same central population. So let me sort of draw that in here. So if the null hypothesis were true, right? If the null hypothesis were true, then our sample means are going to mostly fall between these two plus or minus 2 standard deviations from the sampling mean. But if the alternate hypothesis is actually true, that is, our behavior is somehow altered, well, then it's going to fall out here into this region, right? Or maybe it falls out here into this region, sort of this uncommon or rare zone. And in that case, if that's the case, then we're going to reject the null hypothesis and conclude that indeed our samples come from different populations, right? But this is all based on the fact that this sampling distribution is normal, and we get that from the